So let's get started. First, hello to Dr. Trish Stadnik. So today is 13th of January, 2022. Good afternoon, Canada, and good morning or good evening, depending on where you are on this small planet. Today's webinar, a series of core modeling webinar, is on water resources management theme that we have in the core modeling. This thematic group is led by Dr. Trish Stadnik. Dr. Stadnik is Canada Research Chair in Hydrologic Modeling and Associate Professor with Department of Geography at University of Calgary. She has close collaboration with engineering community, especially in Prairie Province, and has a very good knowledge of water management practices that is happening in this part of Canada. Additional to her other research interests, Dr. Stadnik is working on risk-based uncertainties for operational prediction of climate change impact. This includes the work on pan-Canadian domain. The water management team is mainly focused on two specific tasks. The first one is application of existing water management models, such as WEEP, that represent the fidelity and detailed water management model as close as possible to the reality. The second is integrating water management in land models and hydrological models, which is the aim to understand the interaction of our inference of hydrological processes and their interconnection with human activities, which is actually much work is needed to be done there. Often our inference of hydrological processes heavily lies on calibration, increasingly difficult with human activities. And it's important to see how reliable these inference are for the future climate scenarios and changes on their human activities or human activity changes in the future. I'm also personally involved in this team, so I'm looking forward to Trish's presentation. Finally, I would like to thank everybody here on behalf of core modeling management team, Dr. Al Petroniro, Dr. Martin Clark, Joy Mitsugiani, and me, myself, and I, Shalom Arabi. Trish, the floor is yours.
Thanks for the kind introduction, Shervan. Can you hear me okay?
Yes.
All right, I switched my mic, so you never know how these things in the land of Zoom or whatever platform we're on go. It's a pleasure to update all of you on the progress for our Global Water Futures Core Modeling Water Resource Management team. That's quite a mouthful. Basically, the way I structured this presentation is I'll pick it up where I left off last time. So some of you may or may not have seen my previous presentations, and if you have any questions about anything we've done, feel free to ask. I'm presenting today from the land known as Mohkinstsis, as it's called in traditional Blackfoot, which means where the Bow meets the Elbow River. Today, we know this place as the city of Calgary. So without further ado, I'd like to introduce the core modeling water resource management team, starting with the modelers themselves. Today is a presentation of their work and their dedication to this project, and I certainly wouldn't have any results to show if it wasn't for the hard work of all of these. Starting, of course, with Shervan's work. He's responsible for the mizuRoute results and modeling that I'll be showing. Fuad Yassin, who's responsible for mesh modeling results. Andrew Tufts, who's worked on the HYPE results. Layla, who's worked on the ModSim integrated water resource management and socio-economic and policy scenarios, as well as Hamid Ghazini, who's worked on ModSim on the Manitoba side of things, so on the downstream side of the Saskatchewan River Basin. With lots of contributions from others, not to be forgotten in terms of the supervisors. It doesn't mean that they've done any less, they just haven't done the modeling, and I put the modelers up front and center. So, as Shervan had indicated, he did a really nice job of introducing the importance of what we're doing here. Modeling has always been fundamental to Global Water Futures. Predicting water futures is one of their primary goals and missions of this particular program. We need to predict both climate change and human regulation, though, if we want our models to accurately capture water resources supply under future climates. So I've adapted this statement a little bit, namely that if we really wish to meet the Global Water Futures goal of improving prediction of water resources, we must account for the landscape scale changes, including those that are imposed by human alteration of the flow regime. And I will define what that actually means. So our goal on the core modeling team is to develop these tools tools that are suitable for operations and research on continental scales, specifically on a pan-Canadian basis. So this is our core team scope. You can see a very large continental basin here. And I would actually argue our scope is even larger than this, because when I was putting the presentation together, Shervan very kindly provided some global simulation results. So I don't know that there's any limit to our scope. A key task up until now has been to specifically improve the representation of lakes in land and hydrology models. This includes the representation of small lakes, which would what we would define as subgrid lakes that aren't necessarily represented as objects on the river network, as well as large lakes that might comprise multiple grids within a model or multiple subbasins or subbasin outlets, as well as managed lakes, so those that we would call reservoirs or dams. We also endeavor to explicitly represent water diversions and irrigation, so abstractions and irrigation. I'm going to talk a little bit about that today. And that has been, up until now, the core component of what we've been doing for the first couple of years, is really developing those capabilities within the models. Once that development is done, which is our current state and stage, then the idea is to conduct a detailed comparison between the different types of strategies of including these lake objects within the models, as well as the mitigation or alteration by people on the landscape, so how we control the outflow, to see where we get the best results and what seems to be the most promising to satisfy a number of criteria that we've identified. So this is the slide that was presented at the meeting in December for core modeling. It's kind of the summary of the progress that we've made in 2020, 2021. Let's see, I'll just put on my pointer here. So hopefully you can see that. So starting with our primary goals, Shervan also already outlined those. The idea was to integrate water management rules in both land surface models as well as hydrology models, but to also do the same from an integrated water management framework perspective. So kind of taking a three-pronged approach to embedding water management in there. We have several work packages that we identified that tackle that on the individual modeling basis. So the first was dealing with the land models. That's largely Shervan's work. Then including water management into hydrologic models on a more regional scale. That's Andrew Tefts and Fuad Yassin. Then integrating decision scenarios and water management into an integrated water resource management model, ModSim, that was developed under IMPC. And then to adapt some of the integrated water resource management models for cold region stuff, which is work that is largely happening out of the University of Manitoba. So achievements that we've gotten to up until now that underpin the results that I'll show today include a global network routing product, mizuRoute, that is part of the Earth System Modeling community, 2 code frameworks that are embedded within hydrologic models, but are largely intended to be model agnostic, that look at managed reservoirs on a regional scale, specifically across the prairie basins, an integrated water resource management model for the Nelson River, right from the headwaters to the downstream outlets into Hudson Bay, with some socioeconomic and policy scenarios, as well as the development of some 3D rating curves to help improve the simulation of ice cover and ice affected stream flow in the winter months for the Manitoba hydro system. So that's all work that has been completed that largely feeds into the results that I'll be showing you today. The focus for today, however, is on integration. So now that our models are developed and up and running, the focus has turned to testing a variety of different approaches and assessing the advantages and disadvantages of the different approaches, as well as leveraging individual strengths of each approach while trying to diminish the weaknesses of the different approaches. And I'll explain what I mean by that. Starting with the global land surface model, which would be mizuRoute, that has some regional water management rules embedded within it. So network routing is efficient on a global scale. However, it often lacks the local accuracy or local knowledge to do with reservoir operations. So by taking the regional rules that were developed with the hydrology models and embedding them within the global model, then we can achieve a better representation of some of the local operations that are happening. Counter to that, but also in parallel, we are also scaling up some of our regional approaches to a continental scale. We're not yet at the global scale, but we're working our way to pan-Arctic. We have achieved continental scale. And we're basically taking these water management rules, these simplified water management rules that have some regional knowledge and complexity, and we're scaling them out and up across continental scales to model the effects of reservoir regulation, irrigation, dams, and interbasin diversions on streamflow. We can then take these first two and use them to develop and derive or inform scenarios for the integrated water resource management model, which is a completely different approach to looking at water resource management on a regional scale for the Nelson River, specifically the Saskatchewan River, and then the lower Nelson from two different ModSim models. And we can derive a bunch of scenarios from the climate hydrology and then couple those with policy and economics to try to get some ideas of how both the hydrology is changing as well as the human decision-making or influence over policy and socioeconomics. And so that's what I'll focus on today, is updating you on these three goals. Starting with the global land surface model, mizuRoute is a vector-based routing model. It is designed for regional and global applications, and it is now part of the Earth System Community Modeling Portal, as I previously mentioned, and the link to the GitHub is provided there. mizuRoute has been run with both Mesh and Hype, as well as some other runoff-based products, which I'll talk about throughout the presentation. It's computationally efficient. Parallelization of the simulation based on decomposition of the river network topology has been accomplished over the last year. And it is host model agnostic. So that's a very fancy way of saying we can take runoff from any product and run it with a mizuRoute configuration. And now, thanks to Shervan, it has the capability for lakes and reservoirs in multi-model configurations. And so that's exactly what we've done, is made this like a plug and play approach. We have the mizuRoute routing model, and we can plug in different descriptions of lakes and reservoirs and test the outcome. So these are results from the mizuRoute global application, courtesy of Shervan. It simulates streamflow globally, both with and without lakes. And we can check the impact that lakes and reservoirs have on the river network, both globally as well as regionally, particularly looking at what happens on the downstream side. In this particular simulation, a single lake model was used. They were all treated as natural lakes. So that would be if we don't have any data on the outflow, then we just let the system run in a natural state. And they were used from the Dahl formation. The result is from the lake and river network topology based on the resolvable lakes from HDMA and hydro lakes. And it describes or includes 4,200 lakes globally and 7 resolvable lakes within the Saskatchewan River Basin, which is shown in the lower left corner here as an inset. And that's important because we're going to zoom in on that in a moment and look at a case study there. The runoff was provided from CLM at a resolution of 0.5 degrees and remapped to the HDMA subbasins using the mizuRoute mapping capabilities. And what we're showing here are the NSE differences for influenced river segments, streamflow. The darkest colors represent closer to Nash of 0.5 and below, and the lighter ones are closer to 1. So it's clear from looking at something like this that we can apply such a product on a much larger scale to look at much larger consequences and continental scale influences of managed resources and lakes. And we can also see that as we move downstream in some heavily managed systems, the effects of the dams are diminished. So there's somewhat of a diffusive effect, which has been reported in literature before. And this is something that we can test when we look closer at the regional scale. So zooming in from global to regional, and now taking a look at the South Saskatchewan River Basin, then runoff is still provided by the CLM model at 0.5 degrees and remapped to merit hydro subbasins, which are corrected for the lakes and reservoirs using EasyMore. We can zoom in on two particular parts of this basin and take a closer look at the river networks. So this area and this area side by side, you can see the kind of detail that this is capturing. So 7 of the lakes are captured that have height parameterizations within this region, as well as 1 lake, Lake Diefenbaker, shown on the right-hand side here on the downstream side of the basin, that has a more complicated lake parameterization, a hyperparameter model from the Hanasaki configuration. And we're going to talk about that next. So using the merit multi-model capability, the whole intent here was to evaluate the impact of alternative model configurations for simulating the lakes and reservoirs within this river network. So when a different product was used, then 70 resolvable lakes for merit hydro and hydro lakes were achieved in comparison to the 7 within this basin from the HDMA and hydro lakes. The symbols are shown on the diagram here on the left-hand side. We can then compare the simulations using increasing model complexity. So for instance, looking at the DAL configuration, which is treating all the lakes as natural lakes, then using the 11 hype lakes within this basin that are included, and then adding the Hanasaki configuration for the 1 downstream lake, which is Diefenbaker, shown on the right-hand side. And so it's an increase in the amount of complexity added to the model. We can compare and contrast the accuracy of the output that we get by doing that. And so by comparing the results for the lake parameterization, using these 3 levels of complexity, so all lakes are natural except for the 11 lakes modeled by the HYPE regional model, and then all natural lakes, the 10 HYPE lakes and 1 Hanasaki lake. Then we can see how closely we come to matching the observations, which are shown in the dashed black line. For streamflow as well as for lake storage. And this is showing Diefenbaker. For the lake storage, it's right in the lake. For the streamflow, it's further downstream near Saskatoon. And starting with the least complex model, of course, the farthest from the observations, and increasing in terms of matching the observations as we increase in model complexity. So clearly model complexity does have an impact on our ability to simulate complex systems that are managed. The question is, can we actually do better than this, or do we just calibrate our way out of the problem? And I think that's a bit of a rhetorical question, but I'll leave that to Shervin to answer if there's any questions on that. How can we actually apply this type of modeling to take a better look at operational outcomes? So this is an example of mizuRoute's data-driven capability using scenarios for operations of Lake Diefenbaker during the June 2013 flood event. There's no host model in this case. The river network is data-driven, which means that it can be based on water management nodes and connections. The majority of the model is actually fed by upstream gauges that you see here, as well as the diversion for the Capel and the actual scenarios of changes in lake level and lake storage. So first, the model is calibrated for historic data to adjust the model diffusivity and the velocity. Then the parameters are forced under various scenarios, which represent the different lead times or time of action, initial conditions of the reservoir in terms of the elevation and water surface level, and rate of accumulation, so the change in the storage and water level. And the water level scenarios can be built upon any approach whatsoever, including through machine learning. The scenarios you're seeing here are largely theoretical, but we could use firsthand knowledge to help inform the type of scenarios that we would test in the model to say, well, if we made this decision, what would be the outcome? And we could relatively quickly derive a forecast for different decisions for a lake such as Diefenbaker, which provides critical flood protection for the downstream side in the province of Manitoba. So in some of these scenarios, you can see that the flood is fully stored due to the high rate of accumulation within the reservoir. The question is this just theoretical or is this actually possible? And these are the kinds of questions that firsthand knowledge really helps with. So some scenarios can be enhanced by the experts that are actually operating these areas, and there's potential machine learning applications here. So some of the future directions for this work include testing more lake and reservoir formulations and embedding those into the mizuRoute model, applying the model framework in various operational settings and scenarios. Certainly an emphasis on gathering more local and regional knowledge of the reservoirs and their operations, and particularly the operational scenarios that are of interest, and applying the model under different contexts, both to answer science questions or research questions, as well as to look at operational case studies. For the last one, the infrastructure is ready, and this can be accommodated within the integrated water resource management model now, and that's what we're starting to work towards. Of course, though, gathering data and information for these reservoirs is an onerous task, but it's really key to the outcomes here. But it requires integration of global scale efficiency as well as the local knowledge. So we are interested in exploring different ways to leverage the computational efficiency of approaches such as mizuRoute and the numerics on a global scale, but to increase the accuracy of the description of the water management processes and reservoirs using some of the regional approaches that have been developed in the hydrologic models, such as MESH and HYPE. And so we can use the regional information for the reservoirs themselves and the reservoir outflows, and then feed that back into mizuRoute to accomplish an integration between these two methodologies. The advantage here is that you can mix and match the different scales and leverage the computational efficiency on a much larger scale to evaluate the true downstream and interbasin impacts of upstream decisions. We are also doing somewhat of the opposite, which is scaling up some of our regional water management rules to apply them on a continental scale. And so what you're seeing here are some of the results of the HYPE reservoir model applied pan-Canadian, so across all of Canada, to look at the impacts of reservoirs and dams within the model in terms of improving the model outcomes. So the King-Gupta efficiency as well as the change relative to the baseline. So the baseline would be having no reservoirs, and then the change is due to the influence of the reservoirs. And here we can see that there's strong performance, so KG is greater than 0.5 and much smaller variability errors in some of the largest rivers that have regulated influence, including the Mackenzie and the Yukon rivers, so up in this region here. Regulation certainly improves the modeling outcomes for other smaller rivers that have significant regulations, such as the Moose, the Nelson, and the Churchill rivers. And it reduces errors and variability generally across Nelson and Mackenzie rivers, anywhere from 10 to 70%. There are still some problem areas. A lot of that has to do with trying to apply a region-specific model on a much larger scale. So either way you go, you have problems that are encountered, but this is just one more tool that we can add to the toolbox. But it's more than just reservoirs that we have to look at when we talk about water management. It's also important to consider, particularly across Palliser's Triangle in the prairies, the irrigation and abstractions. They can have a sizable impact on the outflows that we see. So Fouad from the University of Saskatchewan has done some work to evaluate the impacts of irrigation and abstraction in the Saskatchewan River Basin. The zoomed in region and the figure on the left up here shows the irrigation districts within parts of Alberta and Saskatchewan. And then the watershed map or basin map for the South Saskatchewan River. The far right top figure here shows the difference between two different schemes that were added for accounting for local abstractions, main abstraction at a point or a local grid cell abstraction to account for irrigation water supply. The main abstraction, which is a point below the reservoirs, provides a better and more reliable water supply throughout the year. So the blue bars are bigger and extract more water. The local grid cell method indicates minimal water availability in general. The method that was finally implemented was a combination between the two, where irrigated tiles within irrigation districts will receive water from a main channel abstraction point located below the reservoirs, and the irrigation tiles outside the irrigation districts receive the local grid cell abstracted water. And just so you can see the influence this has on the model, the bottom right figure looks at a comparison of annual evapotranspiration for irrigated simulations versus no irrigation. And you can see that certainly it has a significant impact on the amount of water that's lost through evapotranspiration, which is anticipated, and so that's good. And it certainly changes the water consumption. So deviating from the one-to-one line slope and certainly changing the mean and median loss of evapotranspiration by about 26 and 29% respectively. Most of the increases are observed for irrigation tiles located within the irrigation districts. The outside tiles have a lower impact, which we would have expected from the abstraction losses here. But conducting change assessment to really understand how these kinds of local scale, both in time and space, changes have an influence when we then couple with climate scenarios really requires that we have a better understanding of what the system was like before it was ever even regulated. So one of the things our team has really been focusing on is developing what we call renaturalized scenarios. I don't like calling them naturalized because I don't think you can ever take anything back to its true natural state, but attempting to renaturalize it more so. We've developed these scenarios for mesh and hype, and what I'm showing here is the work from Fouad for the South Saskatchewan River Basin, where he has done this, developed a renaturalized streamflow scenario for 53 stations and compared that to an AEP, Alberta Environment and Parks, renaturalized or naturalized streamflow data set that's been generated and downloaded. These simulations are conducted at a daily scale, but aggregated to weekly for model evaluation. And here are the results. When we compare to the AEP naturalized data set, it shows general strong performance by Nash-Sutcliffe and KGE error statistics for 40 stations for a period from 2002 to 2009. So that kind of highlights why this is so important, because a lot of these tributaries are now regulated in modern day times. And so the only way that we could compare to an unaltered state is if we run it in the model world or the simulation world. And that really gives us a true sense of how much the system has changed over time. So blue in these diagrams represents a better fit with the observations, and most gauges generally are performing well. And note that this evaluation period did include some extreme years like drought years in 2002, 2003, and a very wet year in 2005. And so the results differ. You can see for the Old Man River at Lethbridge shows very good fitting overall. And similarly for the Bow at Banff, with more limitations of the underestimation of the recession, which is largely due to the glacier model and glacier contributions. But on the other hand, we do see underestimations for instance, the Belly River and near Mountain View, and overestimations for the Cascade River here. So, not perfect by any means, but certainly better than having nothing in terms of how much the system has changed. And once again, we're also scaling up these approaches using the HYPE model. The diagram on the left shows you all the domains in which we've produced renaturalized streamflow scenarios. So that's for the Nelson Churchill River on the western side of Hudson Bay and the La Grande River on the eastern side. This was of particular interest to our hydropower partners to get a sense for how much their regulation has influenced the systems. And so we've generated this with the HYPE model. You can see the diagrams on the right show the outflow in comparison to the observed time series. And so generally the model's doing quite well. The way in which we develop these scenarios is we take a model with all this regulation in it, including the irrigation, the lakes, the diversions, and then we strip it all back. So we ask a grad student to undo all the work that they've done, which is a thankless job, I think. And then we run it in a naturalized state. And in this case, we have actually also altered the land cover to an unflooded or pre-flooded state as well. And the results kind of tell the story for themselves. So relative to what we've done here is compared to a pre-development period of observed streamflow versus a post-development period. That's the gray and the black lines respectively. And then you can see the regulated model versus the renaturalized or naturalized model during both periods. And in some cases, you can distinctly see, even from the observed streamflows, the complete reversal of the seasonal cycle that's occurred due to regulation. And in some cases, the models are doing quite well at capturing both states. And then in other cases, we have more work to do to help describe the regulation within the model. But generally speaking, we're capturing those pre and post development cycles. So that brings me now to an entirely different approach, which is the integrated water resource management model. ModSim has been developed for the Saskatchewan River Basin and similarly on the downstream side in the province of Manitoba. Historically, it was driven with observed flows under the IMPC project. And so where core modeling now differs is that we're coupling it with some of the runoff and hydrologic products that I've just shown here. And so the idea is to test the integrated water resource management model with a variety of different scenarios, starting with the climate and hydrology. So if we just zoom in on that one box, what we're essentially doing is mixing and matching different scenarios from mesh, HYPE, or the combined land surface model, which is mizuRoute, and hydrologic model with the water resource management rules embedded in it. And so we can plug any one of those in to describe the hydrology. We can do that for historic and or future time periods. And we can also now do that for the regulated state, which is the current state of the system, or a renaturalized state, pretending that it's modern day climate conditions, but as if that regulation had never been built, to see how much water supply there would have been had we not messed up the water cycle. And so we can put all of that into the water resources management model, ModSim, and then we can drive ModSim with different socioeconomic and policy scenarios as well. And so I'm actually going to talk about that a little bit today. And this is the work of Leila Aman and Simon Rizavi from University of Saskatchewan. So these socioeconomic and policy scenarios were informed or designed by Haley Carlson and Pat Gober through the IMPC project. There's three main groups of future scenarios that were considered, including a mix of different crops and crop types, which you see in yellow. Irrigation expansion due to the announcement in Saskatchewan that they were going to expand the irrigation capacity of the province. A similar announcement was also made in 2020 in the province of Alberta, though that's not considered here. That's something that we're talking about including in future scenarios. And last but not least, improving the irrigation efficiency shown in red. So if we can actually improve the technology and how we irrigate these croplands. Last, shown in blue, are mix and match of scenarios using a combination of different approaches. These are all for historic periods still, and one type of historic observed runoff scenario. But of course, future work would be to run this with climate scenarios and also to run it with a variety of different hydrologic scenarios as well. These results are from the integrated water resource management model, ModSim model, for the Saskatchewan for two subbasins, one in Alberta, the upstream side, and one on the downstream side in Saskatchewan. You can see on the downstream side that the irrigation water supply has certainly changed with the different scenarios. That's to be expected given the irrigation expansion is actually occurring in Saskatchewan. So we see minimal change in Alberta because the irrigation expansion for Alberta isn't yet included in the model. And Alberta is planning its irrigation expansion. So once that's included, we would expect to see larger differences. And then certainly this is reflected also in the potential water shortages that would result for the basin, with the upstream in Alberta being largely less impacted or less influenced than the downstream side with irrigation versus non-irrigation shortages in Saskatchewan. So the whole advantage of a system like this, and we're just getting to the point, these are the very first simulations that have been developed, is that we can really look at a host of different factors influencing things like water supply shortage and evaluate a priori the policies that are being implemented and the decisions that are being made before it's too late to roll back our decisions, hopefully. However, a wise Canadian hydrologist once said, and I was reminded of this quote this week, and I would have been remiss if I didn't include it: ask not if our models are good enough, but what are our models good for? So that is a quote that Paul Whitfield has been cited as saying. And I think it's really good for us to take a step back from all this complexity and say, but why are we doing this? And is anybody actually going to use this? So I like to think of this as our attempt at bridging two worlds, which is putting the theory into the practice and saying, is anyone actually going to use what we're developing? Is it useful? So certainly in principle it is, but there's a few things that need to be considered here before they can be used operationally. The Lake Diefenbaker operations example presented earlier from Shervan's work in mizuRoute was a good example of the information content that models can provide that would aid forecasters in understanding the system. But operational models have even more specific needs. They don't really want to evaluate theoretical scenarios. They need to be able to run the models very quickly, and they have to be computationally efficient. They also need to be user-friendly. Many consultants and operators are still using spreadsheets to do their forecasts. So we have a huge gap to fill here in terms of introducing technologies such as integrated water resource management models or even network routing models. Hence why many of these methods have yet to be implemented, but there are many examples were in cases where these kinds of technologies have been implemented. And that's what I'm going to show next, are some case studies from Manitoba Hydro, where they are using the integrated water resource management for forecasting water supply and lake storage, as well as ice conditions. So this is the Manitoba Hydro water supply or basin water supply. The example that I'm going to show first is from the Winnipeg River Basin, which represents about a total of 40% of their water supply energy supply in total, which originates near Thunder Bay, Ontario, drains into Lake of the Woods, and then eventually into Lake Winnipeg, and then out through the Nelson River here, which is the lower Nelson generating complex, out into Hudson Bay. This is a very important basin, and it also includes two inflow diversions from Ontario that OPG and Manitoba Hydro co-operate. So industry partnerships were really crucial in being able to set up this model. And so this is the schematic diagram of the Winnipeg River portion feeding into Lake Winnipeg, and then the lower Nelson generating complex that feeds out to Hudson Bay. Input data was provided by Manitoba Hydro and Ontario Power Generation, such as efficiency curves for the power stations, tailwater rating curves, lake mapping characteristics and minimum forebay levels, outlet rating curves and forebay elevations, stage storage curves for all the lakes and power stations, as well as daily time series like elevations, inflows, outflows, and hydropower generation. So none of this work can happen without the partnerships. The biggest lakes in the two branches that feed the Winnipeg River from Ontario include Lac Seul and Lake of the Woods, which are represented in the greenish yellow here. And they're really integral to the operation of the system, particularly Lake of the Woods, which is often used as a swing lake to help increase storage or increase generation capacity on the downstream Winnipeg River, which is where all the generating stations within the Winnipeg complex reside. The model was evaluated both in terms of comparing simulated and observed outflow from the generating station points, as well as hydropower generation. And so the ModSim optimization results are shown here on this slide. We can see from the table of root mean square error, p-bias, and NSE that the model fairly accurately simulates branch 1 and the Winnipeg River, but then in turn struggles to simulate branch 2. So there seems to be a trade-off there, and that's not surprising. Branch 2 is largely influenced by Lake of the Woods, and Lake of the Woods has some very specific rating curves and operations that are happening. It's often been described to me by Manitoba Hydro people as somebody sitting there with their hand on the throttle and just going like this all day. So there's some goals over the next year or so, which is to add the tailwater rating curves of the Winnipeg River stations, to add more description of Lake of the Woods operation, running the model based on target storages, and hydro generation as well. The next thing, or another use of the integrated water resource management model that Manitoba Hydro has been playing with, is for their ice stabilization forecasts. So this was the Winnipeg River system feeding into Lake Winnipeg. And if we come up through Lake Winnipeg, then we hit the GenPeg generating station. And it's the first generating station at the outlet of Lake Winnipeg. And it's highly influenced by ice formation each year. And there's a large ice stabilization program that has been in place since the 1970s due to frazzle ice formation. And this is a big component of making sure that Manitoba Hydro can generate throughout the winter when the loads are the highest. And one of the tricks has been that notoriously, the models that they've used don't account for the ice-affected discharge or ice-affected rating curves. And so some 3D backwater rating curves were used to estimate the channel flows during the freeze-up period. And they were embedded within the integrated water resource management model for this GenPeg node, as well as the Notigi node, which represents the diversion from the Churchill River down into the lower Nelson River. And when those curves were added, we saw significant improvement in our ability to capture the measured flow, which is shown in the dark blue, relative to our corrected simulated flow using our simulated ice factors as well as the 3D rating curves. And the simulated ice factors were developed in conjunction with the Manitoba Hydro partners that really helped to describe how the ice formed and what the changes in the roughness were through their monitoring program. So a summary of the deliverables that our team has promised by 2023. We promised continental scale network routing that includes lakes, wetlands, reservoir regulation, diversions. I put a check mark there because we've delivered on that. Thanks to Sherban and the group, we have a global routing product. Codes for embedding reservoir regulation into hydrology models designed to run with minimal input data. I've also put a check mark there. We've developed and tested one code with mesh model and one separate code, but very similar in terms of its conceptualization with the height model. And they're designed to be relatively independent and run with minimal input data. So where our focus is now and going forward for the last year of this, hard to believe that we're on our last year, is to really look at the dynamic climate hydrologic integrated water resource management scenarios using a variety of different decision points. So different hydrology and runoff, different climates, historic future, as well as the regulated versus renaturalized scenarios, and then the socio-hydrology aspect, which is the socio-economic, as well as policy decisions. So what's in our future? To sum up our work, our priority is definitely on the methods of incorporating water management into a variety of different models and helping to make those model agnostic. So flexible in design, computationally efficient, regionally accurate for their process descriptions, and integrating as much local knowledge as possible. The water management scenarios must also include a multifaceted decision space if we hope to get this right to aid with operations. So climate-driven hydrologic changes, socioeconomic and political changes, as well as our human response and decision-making, such as the operation of certain reservoirs at certain key nodes. And on modeling uncertainty, I leave you with this. This is an excerpt from World War II, when weather forecasts were being generated for the troops. And it says, the statisticians among us subjected these forecasts to verification, and they differed in no way from chance. The forecasters themselves were convinced and requested that the forecast be discontinued. The reply read approximately like this: the commanding general is well aware that the forecasts are no good. However, he needs them for planning purposes. So just a reminder that if we're producing something relevant, it will be used, and that it's really important to make sure that we're producing something that's useful. So that's it. Here's a summary of the publications that our team's produced thus far, and I'll open the floor to questions, I guess.
Excellent. We are on time. Thank you, Trish, for the very, very nice and elaborated presentation. It's very nice to see that, well, the last year things are coming together and we are moving toward what was promised. We can achieve that as well. So fingers crossed for 2022 and a bit of 2023. So the floor is open to questions. If there is any question, you can put it in the question and answer or chat, and then I will read it here. And we can just give it 1 minute, maybe. Well, if not, I have actually a question, but I want to be the last.
Looks like there's one from Roy.
Yeah. Oh, excellent. I see. Roy Brower, one way to account for trade-offs is to use scenarios, as you seem to do. Are you able to model trade-offs in the model self too?
Yeah. So I think what you're getting at is like different decisions about the model structure. And that's largely the results that I showed from Shervan's work, actually, with mizuRoute testing different lake parameterizations or lake configurations and looking at the advantages and disadvantages of one approach over another. So the least complex, I'm assuming, has the quickest runtime and is the easiest to implement. The most complex takes the most time to implement, but is there the value in doing so? And I think that's what you mean by evaluating model trade-offs. And then certainly expanding that work to look at all the different possible configurations. So what is the advantage of using the integrated water resource management model over the land surface model embedded with the hydrologic models, or what is the advantage of using the hydrologic models at a regional scale versus the disadvantage of that? And so that's really how the whole team has taken this approach. If that doesn't answer your question, feel free to elaborate.
We have two more questions, one from Wouter Knoven and the other one from Pravin Rokaya. John also asked a question. So I go with Wouter. He was second. Hi, Trish. Good stuff. Building on that quote from Paul, are there concrete plans on model evaluation approaches that go beyond looking at aggregated efficiency scores and dive deeper into what is my model good for question?
Yeah. So the short answer to that is probably we don't have enough time within core water resource management modeling in the next year, but certainly knowing me, and that's probably why you asked the question, that is always at the heart of what I do. That's why I really liked Fuad's presentation of the results with the irrigation abstraction, because he took it down to the process level, which is looking at the evapotranspiration. So again, always mindful that there's never any one best model. It really depends on the purpose or the intent of the modeling exercise. And if you're looking at this for agriculture, looking at evapotranspiration water loss and comparing the models on that basis is probably more useful than even looking at streamflow outcomes. So indirectly, yes, though not a core part of our mission, I would say.
I hope Wouter is satisfied with the answer. If you have more questions, just feel free to write it there. The next, which is quite interesting, from Pravin Rokaya. Great presentation, Trish. Can you please talk more on bridging the gap between research and practice and how the GWF could potentially help local agencies who have institutional human capacity and technological barriers? Thank you.
I'm laughing because that slide was thrown in the presentation after seeing your tweet this week. And the reference to the spreadsheet models, we actually had a talk about that earlier in the week too. And I think it was a really good reminder to us all that, you know, we're doing some great things, but those great things are only great if they're actually used and usable. So from a GWF perspective, there's certainly a lot we can do to help. Part of that is taking people like yourself and planting them in those agencies, because change often happens at the grassroots level from within. But I think another large support that GWF can offer is with technology transfer and training capacity through webinars, but also more specifically through co-op students or student interns and things like that, where you actually do very custom type workshops post-COVID, and you go in and you do training sessions. And I'll be honest, that's the only way that we got Manitoba Hydro up to capacity to use integrated water resource management model on their own, was by spending many hours doing training sessions, showing them at first, and then sitting with them at their laptops and helping them run it. So it was a very hands-on workshop approach. And that's just through many hours and much time commitment. But the payoff's huge, because now they have a group that has that capacity in-house, and now they can do their training in-house. So, I mean, oftentimes from the grassroots level, and that's the approach that it's taking.
I can add to Trish's reply from my side as a developer. Something that I would appreciate very much if those agencies also come to us with some, I'm sure there is links and collaboration already, but I would be happy to hear what is the, basically those barriers or those questions which people are after, which we can solve. For example, the issue with the Lake Diefenbaker, which was, well, basically I made a case study of, was somebody asked somebody, and that somebody asked John, and John asked someone, and someone asked me like 4 years ago, and it was a very good practice because I spent a week on it, and now I can do it with better infrastructure. So those needs, if they are transferred to researchers and researchers are interested, we can think how to accommodate that. I think we have good infrastructure, but just we need to know those questions. So the next question from John Pomeroy. Great webinar. Some reservoirs have no defined operation rules, guarding that. That's true. And drifting rules. And some have changing rules, Upper Bow River. How do you account for the non-stationarity?
Oh, John, you have to hit me with non-stationary. Yeah, this is a big problem. And the reason why I say that is because it's always a question of adding more uncertainty through trying to predict non-stationarity, particularly under future climates, versus, so for instance, the way in which we adapt the operating rules to account for more water supply or less water supply, versus just leaving the operating rules as is today, describing them today and running those same rules and parameterizations into the future, which is largely the stance that the group has taken now, because it's a starting point. I'm not suggesting it's accurate or right. And I'm going to combine two questions here, because I saw Al's question in the chat about AI. And I think, honestly, that's the answer to dealing with non-stationarity in these lake operations and lake parameterizations into the future, is that we have to take it into AI and machine learning, because that's the only way to do it. So we have to train it based on historic decisions, and then hope that the machine learning and AI can adapt for future management decisions. That is certainly something that the hydropower operators are interested in doing. They just don't know where to begin yet. And I don't think we're quite there in the research, because we need to get caught up with just describing the past and current regulation before we can really tackle the non-stationarity aspect. So walk before we run.
Just to add on that, it's also possible, from the infrastructure point of view, it's always possible to move to more data-driven approach, which doesn't need any rules. Or it's also possible to have more hyper parameter, which I'm not in favor of, but more hyper parameter model, which was what actually Fuad has done and also Andrew has done. But the next step would be fully data-driven. And the infrastructure also allows us to change parameter time to time. So basically, we can do it in real time, change it, and move forward. So those are there. We can have a fixed one. We can have a moving one. The question, where do they come from? That's a different question, which, yes, hopefully, expert knowledge, machine learning, those things might be very helpful.
Yeah, and I want to add one more thing, which is the second point to Al's question, is that I think largely right now, a lot of our scenarios are decoupled, is the way I look at it. So even though we're integrating these different scenarios, no, we're not altering the demand in the model from the historic demand based on socioeconomic and policy scenarios in all cases. So some of them have in the irrigation context, but in terms of hydropower demand, we haven't done that yet. We're using historic demand cycles. And certainly that's why these models are needed, is to test the impact that increasing summer demand for air conditioning load would have on hydropower generation, because historically Winnipeg River has been integral to the system because they generate the spring runoff, they store it in Lake Winnipeg, and then they push it through in the winter months. But if that changes and all of a sudden you've got drought in the summer when your demand hits a peak, then you might be in trouble with your system.
Yeah. So I think, Trish, you answered Al's question. I just read it for the audience.
Sure.
Thanks, Trish. I keep wondering if the only way to sort out reservoir operation is through some kind of AI approach, since it's often so subjective. Doesn't summer temperature in Winnipeg change flow because of AC use?
Yeah, I mean, for sure, ACUs.
It doesn't.
Yeah, ACUs will drive it up, will drive the demand up in the summer. But historically, winter is always the highest demand because it's cold.
And Roy wrote more about the question which he posted earlier. These are the model trade-offs, but I was wondering about the possible economic trade-offs to decide where the water should go to support policy and decision-making. Highest value issue.
Yeah.
No need to answer on the spot. I was just curious how to see how possible decision-making mechanisms are integrated in the integrated water management models under competing water claims. The scenarios give indicators of where the water demands might go up, for example, but then there is still a question of how you try to accommodate different increasing demands.
Yeah, so I will just address that to say that that is my primary interest in developing these kinds of system tools, because I think they're badly needed to answer these kinds of really complex, wicked problems that we don't know because they're too multifaceted and multidimensional for us to sort out in our heads. It's a very complex system as it is across the prairies, but then when we start adding in, you know, human decision making layered with climate change, layered with regulation that exists now, regulation for future development. Manitoba Hydro just built a brand new generating station. They're building another one, layered with the changes in demand that Al highlighted, and so on. You can see that this is more than just any one person can sit down and figure out with French curves and a pencil. We really need to have more advanced and sophisticated tools. And I think that industry knows that too. From my conversations with them, they're just very hesitant to dive in because they haven't traditionally had the person power to be able to do so, or the technology to be able to do so. And that's our job. That's incumbent on us to make this accessible, I think. So, yeah.
Excellent. So maybe we wait. Oh, we are at 3 o'clock here in Saskatoon. I think 2 in Calgary. So time to wrap up. Yeah, thank you very much, Trish, for the presentation. Was excellent.
Thanks everyone for tuning in.
Yeah, and I just, before saying goodbye, I just want to say our next meeting or our next webinar will be given by Professor Martin Clark on the advances in geospatial intelligence, and that will be on February 3rd. 2022. So looking forward to that, and have a nice rest of the day, everybody. And the recording of this presentation will be available online on our website shortly. Thank you very much. Have a nice day. Bye.
Bye.